We're going to switch gears a little bit now. The first half of this module was all about sequences and series, and the second half of the module is all about probability, or the number of different outcomes that can occur. And that brings us to the fundamental counting principle. But before we talk about that, I want to talk to you about something called a tree diagram. A tree diagram is a useful tool if we are trying to find all of the different possibilities in choosing specific items. So in this case, we have Bob's Burger Shack, who has 3 different kinds of patties to choose from on the burger, 3 different kinds of cheese, and 2 types of buns. So if each customer just can select one item from each group, so either beef or turkey or black bean, you can't have a combination, either American, Swiss, jalapeno cheddar, my favorite, and either wheat or gluten-free, we're now going to see all of the different ways that you can make a burger at Bob's Burger Shack. So to make a tree diagram, we essentially start just by making 3 branches. And I chose 3 branches because there are 3 kinds of patties. So there's beef, there's turkey, and there's black bean. Then there are 3 kinds of cheese. Now, it could be that I chose a beef patty and chose American or Swiss or jalapeno cheddar. Or a turkey burger, I could have chosen American or Swiss or jalapeno cheddar. Or a black bean burger, American, Swiss, jalapeno cheddar. From there are 2 types of buns. So there's wheat and there's gluten-free. Wheat, gluten-free, etc. Now, it seems very cumbersome to write all of this out, and really it is. And I wouldn't recommend making a tree diagram unless they ask you to list all of the possible outcomes. So essentially, me writing this out is listing the possible outcomes. And the outcomes are that I got a beef burger, American cheese, wheat bread, beef, American, gluten-free, beef, Swiss, wheat, beef, Swiss, gluten-free, beef, jalapeno cheddar, wheat, beef, jalapeno cheddar, gluten-free, etc. Same for turkey, same for black bean. So this is a great way to do it if you actually need to know what every single option is. In terms of how many options there are, you would have to then count them up. So it looks like there are 18 choices. And we have now listed all of the choices. Sometimes you will see a final column that has all of the choices. So B, A, W, B, A, G, etc. I'm not going to do that just for the sake of time and because it wouldn't really add anything to the lesson. But you get the basic idea of what a tree diagram does. Now, tree diagrams are important later on in statistics when we talk about probability in much more detail. This is just sort of an intro to probability. Now, if we only need to know how many options there are and not what the options are, we can use something called the fundamental counting principle. And that principle says that if you have M number of options in your first choice and N number of options in your second choice, just multiply the 2 together and that gives you how many options total. So for instance, here we had the 3 kinds of patties, the 3 kinds of cheese, and the 2 types of buns. And if I take 3 times 3 times 2, I get 18, and I get that answer so much faster than drawing out my tree diagram. So the fundamental counting principle tells us just to multiply. So here we have a math quiz that has 5 multiple choice questions with 4 choices each, and you have 5 true-false questions. How many different ways can you answer the questions on the test? So if you have 5 multiple choice, that means you have 4 choices, and 4 choices, and 4 choices, and 4 choices, and 4 choices. So that's the 5 multiple choice. The 5 true-false, obviously true-false are 2 choices, and I have 5 of them. So I would multiply all of those together. Now before I do that, just as a side note, another way to write it, which is way easier, is that I have 4 choices 5 times, so 4 to the 5th, which is exactly what this is. And then I have 2 choices 5 times as well. So this way, obviously, is a little bit easier. Either way, my product would be 32,768. 32,768. So that's how many choices or how many different ways you could answer a simple 10-question test. Here's another one for us to try together. We have a state license plate that consists of 3 letters followed by 3 numbers, digits 0 to 9. How many plates are possible if repetition of the letters is not allowed? So let's look at the first thing is 3 letters. So how many letters are there? There's 26 letters in the alphabet. So 26 letters, but now the second time I only have 25 letters to choose from because I can't repeat whatever letter I chose here. And my third letter, I only have 24 letters to choose from. The 3 digits, there are 10 and 10 and 10 because it didn't say that numbers could not be duplicated. So now multiplying all of those together, I end up with 15,600,000. So that is how many possibilities given 3 letters and 3 digits, even with the repetition of letters not allowed. If the repetition, let me try again. If the repetition of letters is allowed, well then that's easy. It's just 26 3 times and 10 3 times. So it should be more than this because I have extra letters that I can use. So instead of 15,600,000, I have 17,576,000 different options. Last one, repetition of the letters is allowed, so 26 to the third, but the number may not begin with 0, which means my first digit, there's only 9 choices. The other 2, I have 10 choices. So 26 choices 3 times, 9 choices 1 time, 10 choices 2 times. And that gives me 15,818,400 different options. Here's a similar question for you to try on your own. So try the question, then press play to check your work. So we have a code for an alarm system made up of 2 letters followed by 2 digits. If there are no restrictions on letters or numbers, that would just be 26 squared and 10 squared, which would give me 67,600 different possibilities. However, if the repetition of letters and numbers is not allowed, that would be 26 and then 25 choices, and then 10 choices and 9 choices. So multiplying those together, I have fewer choices, of course. I have 58,500 different possibilities.